But now I'll then, just to give you a kind of, one kind of starting point on theories in general. Now this is not theories in software engineering. I thought I'd just do a kind of a presentation of some different kinds of theories that are available in other disciplines and what those might look like, so that we get a bit of a common reference for what the concept theory could be. And I'll start here. You don't have to read the words here really, but I'll start just with Karl Popper, I would say arguably the greatest philosopher of science. When he says, because this is also a problem that we will encounter today, I think, the concept of theory, the definition of theory, I think that we will probably have different opinions about what a theory can be. So I think that let's try to stay out of the definition discussion as much as we can, but everyone can define theory as they want, and then we'll see where we end up. This is just for this presentation. The definition of theory, according to Karl Popper, is very simple really. It says that theory is any statement, or a scientific theory, is any statement about reality. So if there's, he says that, here are some examples. All orbits of heavenly bodies are circles. That's according to Karl Popper. It's a theory. And what that does...
That's not a theory. That's a statement about celestial mechanics.
Yes, well, bear with Karl Popper.
No, I'm not. You're so right in choosing him. But a theory is something that allows you to refute a statement.
Yes.
That's the essence.
No, well, okay. Let's try to focus on that part then. Here's another one. Whenever a thread is loaded with a weight exceeding that which characterizes the tensile strength of the thread, then it will break. That's another theory according to Karl Popper. So what this does, and what you're into, or what you're pointing at, is what it really does is that it excludes something. It says that all orbits of heavenly bodies, if someone says that they are squares, that would not fit with this world. So if we had a world where the orbits of heavenly bodies were squares, then this theory would not allow it. So if we take all the possible worlds, a world where the orbits are circles or where there are squares.
To be precise, the theory in which that statement is true would not allow the other one also to be true.
Please, Dinis, please, I would like to say that this is a theory. Let's just accept this just for my presentation.
Yeah, okay.
So what we say then is that some theories, they limit the possible worlds. And a really, really precise theory, it limits it a lot. If you say this, for instance, all orbits of heavenly bodies are circles, that limits it more than if you say all orbits of heavenly bodies are ellipses, right? And Popper says that a theory, if it doesn't make any such delimitations, then it's not a scientific theory. If it doesn't talk about the real world and how the real world is, then it's not a scientific theory. But it does. If it does, then it is a scientific theory. So it's a very, in that sense, a quite simple definition of theory. Here's my take on Popper's quality criteria for a theory. Universality, that's how much does a theory talk about? Does it talk about some very detailed thing like the tensile strength of a certain thread, or does it talk about the universe? That's one dimension. There are two kinds of precision. I'll show those later. Precision is how detailed it is. For instance, all orbits of heavenly bodies are circles is more precise than all orbits of heavenly bodies are ellipses, because it says more. Formalization, well, Popper talks about consistency. Formalization and consistency, to me, they're quite related. A formalized theory, it's easier to check if it's consistent or not. And Popper thinks this is a very important criteria. And then corroboration, that has to do with, well, the concept of truth. When we compare it to the real world, when we expose this theory we subject it to trials in the real world, then we will, the harder the tests that the theory passes, the better it is corroborated. So this is Popper's view of theory.
And the point about the red dots, I assume, is that one theory may reflect that, another theory may reflect another positioning.
Yes, that's
but
right.
they're all theories.
Yes.
They're all quantitative measurements that
I would say,
attributes.
according to Popper, when this one goes down here,
Yeah.
then to 0, then it's not a theory anymore. When this one goes down to 0, it's not a theory, and this one.
That's
So when they're 0, then it's not a theory. But if there is something that they say about the real world, then it is a theory. Consistency, that's not that thing.
good. But then you have another, you're making another statement which I think is useful for us. Namely, that if all the red dots should not necessarily be at the right end of the picture.
No.
Is that what you would like to say?
I would say that, well, if they were, then we wouldn't need any science. Then there would be one theory that expresses everything we want with perfect precision.
Thank you.
We would have
Thank you.
one theory
Yeah.
of science. Now I'm going to just give you lots of examples, and this one has been overused. I'll start with it because of that. This is Maxwell's equations. You may have seen them before. We have electric fields and electric displacement fields and so on. We just take a look at the characteristics of this. This is a quite universal theory. It's famous for its unification, the unification that it did. It's not totally universal because it only talks about electromagnetics. So there are a lot of things that it doesn't talk about. So we can't put that at the very top. But it's one of those perfect theories because it is the internal precision, and here I mean that the relationships between these variables are that's very well defined. The external precision, and what I mean is, how do you measure electric fields? How do you measure magnetic fields? That's also very precise. There are exact measurement procedures. And formalization, of course, that's you can't get better than this. And the same with corroboration. This theory has been subjected to lots of empirical trials. We use it every day, and it seems to be correct if there is anything such as a correct theory. Why this is not then at the top of universality? Well, let's take a look at the theory that might be highest on that level, and this is a standard model, they call it, and this is how the universe works. This is a model or a theory over. You got the photons, the Higgs bosons, you got all these basic particles. It integrates the electromagnetic force, the weak force, the strong force. These are 3 of the 4 fundamental forces that we know of. It is quite high then on the universality, but gravitation is missing, so it's missing on that part. And then of course you might say, well, it doesn't say much about, for instance, social phenomena. So there are many things that it has difficulties explaining. When it comes to the precision, it is, some say, well, it is very precise, but some say that, well, this is not the perfect model. We would like to have one with less, they have lots of constants here. They're like, I think there are 90 numerical constants that have been kind of just set to make it work. And so some physicists don't think that's the best, and they're hoping for something more.
Or fewer. Fewer constants.
Yes, fewer. Yes, something more something better.
Yeah.
Yes. And when it comes to corroboration, it's pretty good. It predicts such things as, well, it predicted the W and the Z bosons. It predicted those, and the masses that this predicted were exactly what they found. That's a pretty good prediction to find a new particle like that. But it doesn't explain dark matter, for instance, so there are parts of it that's not perfect. Here's another one, the theory of the Big Bang. The original version, as I found, this is all there is. It's just that sentence. It was published in 1931 by George Lemaitre. All the energy of the universe packed in a few or even a unique quantum. I just want to show you this because this is not very formal. Maybe at least to my dilettante eyes, it doesn't seem to be.
Well, I mean, come on, the definition of energy
Could be.
requires formality. Universe, all of these, yes, but you're still right.
Yes.
It's just that these terms have become household words
Yes.
amongst people like us.
It could be.
But it's true, I like it, yes.
Corroboration is difficult for a Big Bang theory. You cannot subject this to empirical tests, but they're doing their best with adduction. We move from the physics to life sciences. We have the theory of the cell. This is a great theory. In the mid-19th century, they came up with this theory. It says that all living material is made of and functions through cells. That's a pretty nice theory. It also says that these cells multiply by division, and when they divide, hereditary information is passed. This is the basis of this theory. And well, it talks about all life, so universality is quite high. In its common form at least, or I think the form that it's mostly used, and it's not formalized. There's not a mathematical model of this that is this, well, I'm sure there are, but those are not the ones that are used mostly. One interesting thing about it was that it was almost falsified once when they found the axon, the neurons, they're called axons, aren't they? Yeah. They thought that wasn't a cell, and so it almost falsified this theory, but then they realized that it was. Here's another kind of theory. We now move away from in a way, from empirical sciences. Probability theory. That's a theory that says how uncertainty should be treated. It's in a sense a kind of how it. And the funny part about this is that everything is very good with it. It's, you know, it talks about big things. It's very precise. It's formalized. But nobody knows what probability means. So the external precision, how do you measure probability? That's very debated. I didn't know this before I started reading a little bit about probability theory, but it turns out that the frequencies view, that probability is an infinite sequence, or frequency in an infinite sequence. That's not correct, or it is correct according to some, but many say that it's something completely different. That it's, you can for instance say the probability, that's your personal belief. How much you believe in something, that is what probability is. And so because this definition, the mathematics is the same, but the interpretation of how to apply this to the real world, it differs between different communities. So this is a perfect example of low external precision. It's perfect in its own right, but as soon as you apply it to the real world, you find conflict.
So the audience ought to know that the university over there has Per Martin Löf, who got his PhD from Kolmogorov. You know that, of course.
I didn't.
Ah, well, and I'm sure he would exactly support your statement, namely what was it, the external. Yeah. Oh, you should talk with him. He's one of the great.
Now we move from, let's say, the exact sciences to economics, the theory of supply and demand. This is a very famous theory.
I have a point.
Yeah.
The previous one, first of all, I really like your talk. I got it right when I asked you about the red dots, because that's what we see now. This is not an exact science, this is mathematics, period.
Okay.
So that's not a science, okay?
Well, no, it is, I would say this is a scientific theory because it, depending on how you interpret it, but you apply this to the real world frequencies. So,
I think the question is whether you look at it as a mathematician, and then you say it's just mathematics, but when you look at it as some guy from the real world, you would say, what is the mathematics, does the mathematics really fit?
So this discussion that we're having now, that is exactly why this dot is here.
Yeah. That line is there.
Yes.
And the dot is there.
Economics, the theory of demand and supply. This is a pretty big theory also. Everyone knows about it. It's formalized. It has been corroborated in many markets. I think that there's not, actually I can say one thing about this. and it doesn't have really to do with this, because this is just an example. But I have also checked the Google citations for all of these, and they're at the bottom here for at least, well, not all of them, but some of them. Some were so low, actually, that I didn't even put them there. Just to give you a feeling about how they qualify there. Here's another thing, the general theory, it's called the general theory, that's nice also, the general theory of employment, interest, and money. And this is John Maynard Keynes' great theory, which has inspired many state leaders to behave in a particular way, and the central banks of countries, it has had an enormous impact. And it's, I think that the title is quite correct. It states relationships between interest, employment, money, and other things. It's a pretty big theory. This is written in normal, natural language mostly. There are some equations in there, but most of the theory is in natural language. But the natural language is quite precise. It's quite, in that sense, it's not very formalized, but it has some formality.
And it's interesting to see the title, that John Maynard Keynes had no qualms, had no shame. Instead of calling it as it is, a general theory, he called it the general theory.
Yes.
And it's wonderful.
Yes, that's.
But it's good example. Yeah.
Yes. It's also contested. Not everyone believes in Keynes, and therefore on the corroboration, we cannot push that to the very top.
He wouldn't have gotten the Nobel Prize in economics. All the ones who got it have disputed it. That's the interest. Look back at it.
That's
Just read it back.
Pontus, are you intentionally arguing that corroboration is the same as agreement? Because I would argue that those things are very different, that there are lots of things that are very highly corroborated, but you have this bunch of lunatics who, doesn't matter how much evidence they don't believe it.
I noticed that. I mispronounced there.
Okay, that's fine.
Yes.
No, but
corroboration, that's how well a theory passes through tests, empirical tests. It doesn't have to do with the majority. Here's a theory of, and now we're moving into psychology, a theory of human information processing. Schriffen and Schneider, they came up with a model for how the human mind works when it tries to solve problems. Process information.
I'm glad I've never heard about it.
No? Okay, well here you have 4,800 citations. It's not a huge theory, but it's pretty, it's established in its field.
It's a theory.
Yeah,
Yes, that's a theory actually. They didn't, well they'd say, yes, they say a general theory,
Oh, yeah.
but it's a. There are many alternatives to this theory. So that's interesting that in this field, there's not like in Maxwell's equations, there's only Maxwell, there are no competitors there. But in this field, there are competitors. So that's very interesting, I think, from the point of view of software engineering, and this today's and tomorrow's workshop. Here is a theory of the psyche. This is Sigmund Freud's, one of the few drawings that I found that he'd done about the psyche. It's the Ich, that's the ego, I think. S, that's the id, and there's the Über-Ich, that's the superego. This is Freud's theory about how the mind works. You can see here that, well, it has great ambitions. It is not at all precise. There's no mathematics in this. It has been very criticized for its vagueness. And in fact, Karl Popper himself, he stated that this was one example of a theory where you should pull this all the way down to 0, because he said that this is unfalsifiable. It's not a scientific theory. So it's a good example. Well, but it's, and relating to your statement there, it has been very popular though. And as
Much too popular.
yes, many think so, yes.
It's wonderful what you're doing.
Here's a theory of great power politics, and this is one that I like. John Mersheimer, he wrote a book called The Tragedy of Great Power Politics. it's not a very popular theory, but it's not. It's pretty established within the fields of international relation. There are. Here's just you can't see it, but there are many theories that compete with each other in this domain. But these people are very interested in the concept of a general theory, and it's very interesting to read about it because it relates to our workshop. This is more or less the theory. It's just 5 statements like that. That's his theory. But it says he uses this to predict all kinds of historical events and future. So it's a very nice book. And as you can see, it lacks in precision and formalization. There's no equation here, and also in corroboration. It's a nice theory.
I would question the last item.
Huh?
I would question the last item.
You think that's debatable?
Definitely.
Yes. Here's one that I really like. This is a theory of marriage, and it's not anyone who came up with this theory. This is Gary Becker, the Nobel Prize winner. Becker.
Yeah.
It's a big theory in the social sciences. And it's very interesting because, well, this theory, it explains, you can read here, it says, in part 1, I ignored love, that cause of marriage glorified in the American culture. So he writes nicely about marriage, or maybe not. This is the core of his theory. It's very mathematized. It's surprising that this exists. I was very surprised to find it. But but I like it. It has very high internal precision in the sense that, well, it's very formalized.
I want to ask you, it's fascinating. Whatever variables occur there, are these objectively measurable variables?
Good point, because that's this one, external precision. I put that pretty low, because this is based very much on utility theory. And utility theory is about how people value things, preferences. It's difficult to measure. Everybody knows that, and particularly when it comes to the utility of marriage, we can expect to find difficulties in measuring these things.
I asked the question because when I show it to my wife, she will ask, what do you mean by that X? And said, so on. Better be prepared.
Yes.
The problem.
Can you give some examples what some of these numbers would be? Just to get an idea.
All I can say is that Z here, that's the utility. So, and this is based also on rational actor. The idea that people are rational, they are selfish, and they strive to maximize their utility. With this, he explains such things as why one person chooses to marry another one, why people get divorced, polygamy, he says he can explain, how income is distributed in the family, that there are inequalities. He says that his theory can explain many of these things. He didn't get the Nobel Prize for the theory of marriage, but nevertheless, it's
Did he write it before or after?
I think he wrote it before. Yes.
Yeah.
To my astonishment, Gary Becker is still married.
Yeah, I wonder how it will resist the time, because, well, cohabitants we have now. Does this cover the theory of cohabitants?
Yeah, that's true. That's a question of universality, I think.
Partnership, yeah.
Yes, that's a question of universality.
Yeah.
To what extent is this applicable? In what cases? So,
How many variables are there? How many variables are there?
in the theory of marriage, well, actually, I can send you the paper.
Yes.
Would you like to have the paper? I'll send it to you.
I want to have your lecture there. It's a marvelous lecture.
All right.
Yes. Brilliant.
Okay, well, I'm at the end of the lecture almost. Here's some other theories that I've come across. The theory of the growth of the firm. That's a theory about why firms, enterprises grow.
Who is Mr. Penrose?
Well, it's Mrs. Penrose.
It's
well,
not the Penrose.
Mrs. Edith Penrose.
Oh,
Yes. But it's an established theory. A unified theory of income and happiness. How about that one? It's a quite small theory despite its name. A general theory.
There is a equilibrium there?
Income, well, it has to do with the problem that you can note on a national scale, that as income increases, happiness does not. But on the individual scale, when people get richer, they get happier. And there's a conflict there, and this theory is about solving that.
Wonderful.
A general theory of crime. This explains why people become criminals. It's also established in its field. An economic theory of democracy. The theory of the, I came up with this thing, the theory of the final form of human government. Fukuyama, he's a philosopher that's
Very famous.
Very famous, yes. He says that democracy and market economy, that's the end of history.
Yeah.
The germ theory of disease, that's quite a different kind of theory. The general theory of political economy, I put Lenin here. And here you have Adam Smith, of course, with the general theory of economy. One that I like, a theory of organizational structure from Mintzberg. There's a theory of justice, quite recent one also. But there are all kinds of theories. And so the point with this talk is that, well, I have it here. There's more than one way to skin a cat, they say. So there are many kinds of theories, and it's easy to kind of get stuck in our normal ways of seeing theory or thinking of theory, depending on where we come from. If we're engineers, we think of it in one way. Social scientists in another way. So this is just kind of to open up a little bit what theory can be. And also to pose this very open question, what qualities can we expect from a general theory of software engineering? Will that be highly formalized? How universal will it be within the domain of software engineering? How many phenomena will it be able to explain? And so on. So this is just a kind of introduction. Yes?
It's very interesting to set the scene in this way, and I'm stuck with the term general. I think it's very ambitious, and some of these we can show they have by time and by empirical evidence shown their carrying that term general with honor. But I assume you would be able to find hundreds of other general theories that we would laugh at today. So I have problems with that term. What do we put in the term general, connected to general? Because I appreciate very much your universality scale, because I think that's important to scope a theory. But when we introduce the term general, does it mean that we strive for the most universal theory, or is there something else in the term general theory which I haven't caught yet?
Me, I get the feeling that general is a theory that people propose in a field where there are smaller theories and they're trying to propose something larger. I think that's when people use the word general.
Like Einstein's.
So I think that when someone is trying to move up the universality scale, they may apply that. And this is also the workshop today and tomorrow. The attempt to move up a bit here, at least, or to find something perhaps that exists a bit up there, higher up.
May I say something about my feeling about that? Because I had the same feeling when I read the title, General Theory. That sounds ambitious. But then I also looked into what people call theory in the field of software engineering, for example. Then a process model is called a theory. And many things which are just methods are called theory. Then I had the feeling, oh, this is just to lift it up and say, we are talking about real theory and we're not just talking about a method. And that's the way I understood the title of the workshop.
But this discussion, and that's good, illuminates that the word general at the second last line has nothing to do with the term universality. Each of the general theories that one might come up with about software engineering may have their own measure of universality. And that's fine.
Yes.
So, but it's true. Okay.
But what is then in the term general? Are there more or less general theories?
I think he just said it. Take Einstein, when he came with his proposal. Question, did he thereby destroy Newton's theory. In one sense, yes. In another sense, no. Because all the results of Newton's could be derived from the general theory. And then there were some that could not. So it just extended, as he also said, it just expanded. So it became more general. But, okay.
But I think that we will, in the discussion sessions, this is, I think, a topic that will return, because it has to do with what the whole objective of this kind of a general theory of software engineering. What is that? What is it supposed to do?
But I think you contributed tremendously with this survey you gave us, this expose, namely that in the discussion, in the breaks and so on, we might ask ourselves which general theories or theories of software could there be from the point of sociology, from the point of psychology, whatever.
Yes, yes, exactly.
Yeah.
And I think also that, so some of the presentations tomorrow, they will be that. We'll see some different, from different perspectives. It's a nice mix of papers in that sense of what that kind of a theory could be. Ilya?
Do you know any ideal example of a theory to put everything on the right? Would thermodynamic suffice, moving everything to the right?
Which one?
This is thermodynamics.
I think that it has difficulties explaining marriage, for instance, which means that there are things that it cannot explain, and then it doesn't go all the way to the right on the universality scale. But I think Maxwell's equations goes to the right on everything except the universality scale.
It's thermodynamics more universal than...
You don't think so?
The question is university really it answers all questions, or universal within a specific field? Yes. So, of course, I wouldn't expect from Maxwell equation that they explain marriage. Yes.
So exactly, so in this discussion that we will be having, that's the relevant question. Within software engineering, what kind of questions does the theory answer?
Basically, you can use thermodynamics to explain economic.
Mm-hmm.
So it's quite universal.
That's true. I'd be very impressed to see how thermodynamics explains economics.
No,
yeah, I can send you a
he's
link.
right, he's right.
Yeah.
So many things.
The discussion sounds to me as if universality was about how wide the field of the theory is, how wide the domain of the discourse is. Mm-hmm. Whereas generality, I think, as the discussion showed, talks more about how well does it cover this domain of discourse it has chosen.
Yeah.
Yes, that may be. We could have that as a working distinction. Mm. Generality in our case, then that would be universality within software engineering.
Politically speaking, people are afraid to call things theories at all in my discipline because that invites reviewers to complain that it's not really a theory. So everybody calls it a model or a framework. There is no way on earth anybody is getting general theory of anything published in an IS journal. People will freak. There's no point, politically speaking, you just wouldn't put that in a name.
I don't
right?
worry about that. I wouldn't publish in an IS journal, so that's what it's all about. Yeah, you're right. Except that the statement on thermodynamics and economy is so true. You can explain work, energy, entropy, and so on, right, in both cases.
And the informatic as well.
Yeah.
I think that this discussion we lost about generality and universality is more interesting than physics. I think that this is key to our work. I don't think we can come up with any theory on software engineering. I think we have to de-scope and to characterize certain settings, certain types of software, certain types of engineering to be able to come up. I mean, at least we must start in that corner. We cannot start with the most general scope of a theory.
Sometimes you need to follow, if you can't solve the task, make it bigger. So it's the division is not the best.
No,
way.
I mean, if we stay at that level, software engineering is hard. Yes.
Yeah, I mean, you need
That's
to
the theory.
we need to be flexible. I mean,
yeah, if we compare to the field of national economists, for instance, economists are not doing very well at least. nowadays, but they have a fancy tool, they call it ceteris paribus. And that means that when you assume that everything else stays like that, and then you can study these two things. And that would be a bit, but you are actually suggesting that we would become national economists.
Okay.
Just one note. My note about thermodynamics was has some meaning, because maybe when we look at software engineering, we can have something outside software engineering that can be useful. So if we concentrate only on us, I'm not saying that thermodynamics is good for software engineering, I doubt it, but there might be something that is good. And it's not in software engineering right now.
Well, I think another, we use several words, and there come up model, and we could use patterns and other types of things. Kuhn wrote this article in 1962 about paradigms, and I think that's really what we're out after. Paradigms are things that will affect people's thinking, okay? And I think that's what really we're looking at here, how we're going to affect people's thinking about software engineering, rather than providing a general theory of software engineering. So I would think that maybe the right word is paradigm, and that we're talking about a paradigm shift, perhaps, in what we've had as some type of chaotic situation to a somewhat more understandable situation. And that would be a paradigm shift, certainly from the software engineering perspective.
So I'm a little confused, because respective speakers make statements which, when they make them, they make perfect sense to me. Only they're talking about different things. One is talking about engineering, and the other one is talking about a field, say, of science, namely thermodynamics. When we talk about, here we're talking about software engineering. We're not talking about software. Thermodynamics is about, the thermodynamic engineering is about constructing coal-fired power plants and so on. And for that they need the thermodynamics theory. Software engineering, in a sense, hopefully builds on the theory of software, whichever it is, but it's doing engineering. It's just that distinction.
Yeah. But if you don't know the properties of the product we need to produce, somebody needs to create it.
Listen to my talk tomorrow. I can only agree with you.
Okay.
Yes.
We have now caught up with our timetable. So that was a brief success in the morning.
No, you had some guiding lights on because of the people's questions here on the discussions.
Yes. Very good. Very good. So now the real coffee is available for you.
You sent us
outside, just a question of what does it mean?